Intelligent robots with generalizable capabilities are closer than ever before, thanks to Google DeepMind and a coalition of 33 academic labs, which have just unveiled a breakthrough AI solution to redefine the future trajectory of robotics. Importantly, the historical challenge of creating generally capable robots has been that each robot model had to be meticulously tailored for specific tasks, environments, and robot types, with any deviation in a single variable often necessitating an exhaustive overhaul of the training process. But Google DeepMind's ambitious project seeks to upend this paradigm. Their question was clear yet profoundly transformative. Can we amalgamate knowledge from across the robotic spectrum to engender a general-purpose robot? In an audacious leap forward, Google DeepMind, alongside its academic partners, has pooled data sourced from 22 diverse robot types, culminating in the creation of the X-Embodiment dataset. Alongside this, they have rolled out the RT-1-X, a next-generation robotics transformer model. Trained on this extensive dataset, RT-1-X showcases the promising potential of skill transference across a myriad of robot embodiments. Preliminary results underscore the efficacy of this new approach. Google DeepMind tested the RT-1-X model across 5 different research settings, revealing a staggering 50% average enhancement in success rates across a range of robots. This performance metric was benchmarked against models that had been independently and specifically tailored for each robot. Furthermore, the RT-2 variant of the model, post-training on multi-embodiment data, exhibited a 3-fold surge in its real-world robotic capabilities. But Google DeepMind's tech breakthrough also involved the X-Embodiment dataset as its key component. This dataset is an amalgamation of diverse robotic demonstrations, envisioned to train a generalist model capable of navigating varied robot types, comprehending a spectrum of instructions, and exhibiting advanced reasoning for intricate tasks. The dataset is vast, representing over 500 skills, 150,000 tasks, and over 1 million unique workflows, making it unparalleled in its comprehensiveness. Importantly, at the heart of this innovation lies the RT-X model, which stands as the embodiment of Google DeepMind's robotics vision. Building upon their earlier RT models, the RT-1X and RT-2X have been trained using cross-embodiment data. The results are nothing short of revolutionary. Both models not only achieve superior performance, but also display enhanced generalization capabilities, outpacing domain-specific models. The nuanced capabilities of the RT-X model became particularly evident not just with its 50% increase in performance over the competition, but also in the area of its emergent abilities. In fact, some of these emergent capabilities included the RT-2-X model, showcasing an enhanced ability to transfer its knowledge across diverse robots. This was exemplified in tasks involving objects and skills absent in the original RT-2 dataset, but present in datasets for other robots. For instance, it was able to determine that a rock serves as a more effective makeshift hammer than a sheet of paper, and was able to adapt this reasoning throughout various contexts. In another example, the model's refined spatial understanding was revealed, enabling it to discern between nuanced commands such as "move the apple near cloth" versus "move the apple on cloth." These breakthroughs accentuate the untapped potential of integrating data from a spectrum of robots. When incorporated into high-capacity architectures, these models can expand their repertoire of tasks, even if they already possess vast amounts of data. Overall, Google DeepMind's innovative stride reaffirms the feasibility of creating models that can generalize across diverse robotic embodiments, resulting in dramatically improved performance. These advancements aren't just confined to Google DeepMind's laboratories, they resonate globally, echoing across academic institutions worldwide. With future endeavors potentially exploring self-improvement mechanisms and cross-embodiment generalization, the robotics landscape is set to undergo a monumental evolution. Meanwhile, in the second story, another AI breakthrough has been unveiled to create efficient, task-driven perception and planning systems for robots. In order to excel in diverse operations, robots necessitate a 3D representation of their environment that's both semantically rich and compact. Enter ConceptGraphs, an innovative graph-structured representation for 3D scenes for enhanced robot perception and planning. Traditional methodologies, which attempted to integrate features from expansive vision language models into 3D representations, often stumbled upon limitations. They generated per-point feature vector maps, which proved ineffective in broader environments and failed to encapsulate the vital semantic-spatial interrelationships between environmental entities. Such relationships are quintessential for sophisticated planning. The ConceptGraphs solution is distinct in that it harnesses 2D foundation models while ingeniously fusing their outputs to a 3D plane through multi-view association. This seamless fusion means that robots can now familiarize themselves with novel semantic classes, eliminating the need to amass large 3D datasets or undergo tedious model fine-tuning. Delving deeper into its mechanism, ConceptGraphs curates an open vocabulary 3D scene graph sourced from a series of posed RGBD images. Through generic instant segmentation models, regions are segmented from RGB visuals, and each is endowed with a semantic feature vector, subsequently projected onto a 3D point cloud. As these regions are incrementally merged and associated from multiple vantage points, they evolve into 3D objects with affiliated vision and language descriptors. By leveraging advanced vision and language models for captioning, inter-object relations are deciphered, forming the very edges that intertwine these objects into a comprehensive graph. But what truly sets ConceptGraphs apart is its adeptness in converting these 3D scene graphs into coherent textual descriptions, paving the way for task planning rooted in large language models like GPT-4. Demonstrations of ConceptGraphs in action are compelling. Its utility was prominently showcased in robot localization within previously charted environments. By encoding objects using clip embeddings, the system effectively employs a landmark-centric particle filter, relying on cosine similarity for determining particle weights. The outcomes are swift and precise localizations. Furthermore, ConceptGraphs excels in answering text-based open-set queries. The integration of clip embeddings with object-associated text captions aids in handling a vast array of queries. However, for complex, multifaceted queries involving negation or intricate compositions, LLMs like GPT-4 prove more proficient. An illustrative example of ConceptGraphs' prowess involves a robot analyzing an image of basketball legend Michael Jordan. When prompted with the query, something this guy would play with, the robot astutely identifies a basketball within its environment. The real-world applicability of ConceptGraphs was vividly portrayed using the Jackal robot. In a simulated challenge where the robot faced obstructed paths, the system ingeniously queried an LLM to discern which objects could be safely navigated or manipulated. Relying on ConceptGraphs' node captions, the LLM predicted traversability, enabling the Jackal robot to adeptly navigate its environment, avoiding potential obstacles, and reaching its goal seamlessly.